Anything so far? No? Everything is still clear till eigenvalues, eigenvectors? Till here, right? Till here? Okay. Alright, so we will, I thought we'll do the applications now, but then the thing is still getting ready. I will need slides to present the application. So what we will do is we will finish till, we'll finish the theory first till least squares, and then we will spend the rest of the days looking at applications starting from matrix inverses. Okay. So the topic that we will look at today is a small topic but an important one. It's on positive definite matrices first, and then we look at another set of norms, but this time norms of matrices. And we'll first start with positive definite matrices. Okay. Now we know that if you have a vector from Rn, we know one thing for sure, right? Well, we do, x could be any vector, and if I compute something like this, what do I know for sure about, what do I get if I do this? Do I get a matrix or a scalar? Scalar. Okay, what can I say about the scalar? Is there something I can definitely say about the scalar if I do this operation? Yes. Well, I can say this for sure. Okay, I know it will not be negative. Right? If x is not 0, then I know this is definitely true. It will always be positive. Right? That's because this thing is, what is this? What is x transpose x? Yeah, it's inner product, but it's the square of the second norm. Norms are always positive if your vector is non-zero. Okay. So this we know. It turns out another such inequality that is of a lot of practical use is not just the inner product of x with itself, but often we are interested in the inner product of x with some matrix A, or with a vector that is simply transformed by a matrix A. Okay. Of course, here the shape of A is n cross n. Okay. What do I get if I do this? Do I get a scalar or a matrix? No. Multiply it out. Are you sure? This whole thing? Okay. This is a column vector multiplied by a matrix column vector. Yeah, x is a column vector, no? It's a scalar, right? So it turns out often we are interested in the question of, if you have a matrix A and you take any vector x from Rn and you compute this quantity, right? We are often interested in the sign of this quantity irrespective of what x we take. Of course, if you take x to be 0, you get 0. We are not interested in what happens when x is 0. When x is not 0, we want to know what sign does this particular scalar take. Okay. Now, for example, if I had a matrix like this, if let's say A was, okay, what can you say about x transpose Ax? Well, you can take x to be x1, x2, and then from this, can you say anything about the sign of x transpose Ax? Write it out. You're not going to be able to do it by just looking at it. Once you're done with that, what about this? What do you get when you compute x transpose Ax for this matrix? X1 x a okay, x transpose Ax. I'm not asking just Ax. We just did it last time. This was equation for an ellipse. X1, there is no 2 or 4. Yes, it's okay. The 2 is important, right? Okay. From this, can we say anything about the sign of this number? Yeah, it will always be positive. X1 square is always positive. X2 square is positive. Everything will be positive. So for this, we know for sure that this is always positive provided x is not 0. This vector is not 0. What about this? What will you get if you do? Huh? Here? No. You tell me what can we say about, can we say anything about the sign for sure? Are we sure that this will always be positive, always be negative, or always be negative, or it can be positive or negative? Or here, if you choose 1 0, x1 to be 1, x2 to be 0, it will be negative. If you choose 0 1, it will be positive. That means it can be both positive or negative. So we cannot say anything about this. But if this was like this, then what can we say? In this case, for sure this will always be negative, right? But if this was positive, then we cannot say anything about the sign. What about this? That's all? No. Minus x2 square? No. Is that okay? Or no? It's getting cancelled. Okay. Yeah, you're right. This is fine. It's okay. Alright. What can we say about the sign here? Is it always positive? Is it always negative? Can it be 0? It can be, right? If both are equal, then it's 0. If one is greater than the other, positive. If this is greater than this, then it's negative. So here also the sign is something we cannot say, or we cannot be sure about the sign. Okay. And whether or not these quadratic equations in x1 and x2 are positive or negative depends entirely on this matrix A, right? That's simply a property of the matrix A, and that property is what we are interested in, and the specific type of matrices that are of interest are what are called as positive definite matrices. Positive definite matrices are square matrices such that x transpose Ax is always greater than 0 when x is not equal to 0. That's the definition. If x transpose Ax is greater than 0, irrespective of the value, the vector x, provided vector x is not 0, then you say it's a positive definite matrix. Okay? And often you will see people write it like this, but we will not use this convention in this course. A greater than 0, that simply means A is a positive definite matrix, but we won't follow that convention here. Okay. So among these, which of these are positive definite now? I'm going to make this, or in fact, let me do this, minus. Is this A a positive definite matrix? It is, irrespective of what is x1 and x2, this is always positive, so this is a positive definite matrix. What about this? Can we say it's negative definite? We can, right? This is always, no matter what the value of x1 and x2 are, this is always negative. So we can say this is a negative definite matrix. Negative definite matrices are simply matrices whose negative version is positive definite. So we know for sure that negative of this is positive definite. Okay. What about the last one? Yeah, so this is, it's not positive definite, that's all we can say. We can't say anything. Not positive definite. Okay. What about this? No, write down what is x transpose Ax. Well, you don't have to compute, it's simply x1 square. Is this always guaranteed to be positive? Positive when x cannot be 0. Remember x. Okay. What if I choose x to be 0, 1? Is it still positive? No, it's not. 0, 1. See, in fact, this does not depend on x2 at all. So I can choose x2 to be anything I want and choose a non-zero vector, but I'll get 0 here. Right? But one thing is for sure, this will always be greater than or equal to 0. We know that it will never be negative. Right? Again, when x is 0, of course, this is always 0. So that's not interesting. But for this particular matrix, you can choose vectors, non-zero vectors x, for which x transpose Ax can actually be 0, or it will be positive. Okay? And these such matrices where the sign is greater than or equal to 0 for x not equal to 0 are called positive semi-definite matrices. That means x transpose Ax is greater than or equal to 0 when x is not equal to 0. Okay. Positive definite, this is always greater than 0. Positive semi-definite simply means it can be 0 or positive. It cannot be negative. Okay. And this idea, so for example, If that is the case, right, this also means if you think of scalars, for example, the number 5 as a 1 cross 1 matrix, right? You can think of this as a 1 cross 1 matrix. That means the set of all positive real numbers, right, are all positive definite 1 cross 1 matrices, right? So one way to understand what positive definiteness means is in some way the matrix is positive, right? For example, on the real line, all numbers excluding 0 on the right of 0 are positive numbers, right? If we were to ask what are positive matrices, then one way to define them would be like this. There is some of the properties that positive numbers share, these matrices also have those properties, right? That's why sometimes I said people write it like this, that A is greater than 0. Okay? Whereas matrices like this would be non-negative matrices. They can be, the X transpose X can be 0 or positive. Okay? And again, these things have applications in a lot of fields. So for example, one area where this is often useful is in optimization, right? When we are talking about, especially in problems where we are talking about minimizing a function. Okay, I mean the other areas would be in mechanics, robotics, mechanics, in statistics, etc. Okay, let's say we are talking about functions like this, right? Let's say x is a real number. I have a function like this, right? And let's say I have a function like this, a quadratic function. Okay, and I want to know if this function has a minimum. Okay, how would I go about finding that out? This you know from your calculus. Okay, how would you find out if this has a minimum? Okay, so you first differentiate this with respect to what? X, okay. What will you get? Okay, what do we do with the differential? So you find df by dx and then what? Okay, fine, so what? Or let me make it even more general. Let's start with this and then we look at the more general version. Hey, hold on. You differentiate and double differentiate. So you're saying do d square dx square. Hey, hold on. This function. So, okay, the second derivative is always positive. Yes, derivative of e power x is e power x. E power x is a positive, is always a positive quantity. Doesn't matter. E power minus x is always a positive quantity. It's a number above 0. It will reach 0 only when x is minus infinity. That means on the real line it never reaches 0. This is always positive. So does this function have a minimum? How will you find out if a function has a minimum? Oh, okay. Well, you first, to find out if a function has a minimum, if a point, let's say if you have a point x star at which the function assumes the lowest value or minimum value, then the first thing you need to know for sure is at x equals x star, the first derivative is 0. but the first derivative can be 0 for a minimum, maximum or a saddle point. Okay, it does not guarantee that it's a minimum or a maximum, but what guarantees that it's a minimum is if you take the second derivative and at x equals x star, if this is greater than 0, then for sure that is a minimum. Okay, now here this function will have a minimum if a is greater than 0, because the second derivative of f with respect to x is 2a. 2a is greater than 0 only if a is greater than 0, right? So if whenever a, for a function like this, whenever a is greater than 0, then this function has a minimum, and in fact it looks like this. It has a minimum. If a was negative, what will it look like? Well, if it's negative, it will look like this. This function does not have a minimum, it has a maximum. Okay. So in the scalar case, it looks like whether or not the function has a minimum depends on this number a, right? And that number has to be positive, right? One way to write this in this x transpose Ax form, if you think of this as a 1 cross 1 matrix, x is an element from R. You can write it like this, right? Except the transpose has no meaning. It's a scalar, so x transpose is x, and this is simply a scalar. Okay. Extending this to higher dimensions, it turns out if you have this, the higher dimensional version of ax square or x transpose ax, this is a quadratic function in x1, x2, x3, xn, right? This has a minimum, or the shape of this function is like a bowl, if and only if a is positive definite, right? That's where this idea of positive definiteness comes in handy in optimization. If you have a function of this form and you know that a is positive definite, then you know for sure this function has a minimum. A is positive definite. Is a positive definite matrix. If it's positive semi-definite, then you're not sure. But if it's positive definite, then you know for sure that it's got a minimum. Okay. I won't go into the details of. You can look at the slides where the details are worked out for at least a 2 cross 2 case. For example, if you have a matrix like this, A, I think B, C, C. Let's say this is A. Finding out the conditions using calculus is not that easy, but what you will find is the condition for something like this to be positive definite, or a function x transpose Ax to be positive definite, is that this matrix has to be positive definite, or this function to have a minimum, the matrix A has to be positive definite. Okay. And that extends to higher dimensions also. And you can relate this idea of positive definiteness to some of the things that we've studied before. Positive definite matrices have eigenvalues that are all positive. Okay, if you say A is a positive definite matrix, then its eigenvalues have to be positive. Right? You cannot have 0 or negative eigenvalues. If you have 0 or positive eigenvalues, then it's positive semi-definite. The moment it has even a single negative eigenvalue, then it's not positive definite. That's because, for example, let's say the fourth eigenvector or the fourth eigenvalue is negative. Okay, and x4 is the corresponding eigenvector. And let's say lambda 4 is negative, right? So I choose x to be x4 and I do this. I know A times x4 is lambda 4 times x4 because x4 is the eigenvector corresponding to lambda 4. So this will simply be lambda 4 times x4. This is nothing but lambda 4 times x4 transpose x4. This is always positive, but lambda 4 is negative. That means we found an example for a vector where this is negative, that means this is not positive definite. Right? So the eigenvalues are all positive, and it turns out that this is also related to the pivots of, if you remember Gaussian elimination, the pivot elements, the pivots of pivots are all positive. So for example, if you do Gaussian elimination on, well, these are simple matrices, you will find that for this it's always positive. It's anyway in the upper triangular form, it's positive. Here both are negative. Here if you do it, you will find that one pivot is positive, the other pivot is 0. So it will be positive semi-definite. Okay, and that's all you have to, for now you really have to remember. Positive definite matrices are matrices that satisfy this property. If it satisfies this, then it's positive semi-definite. Eigenvalues and how eigenvalues and pivots are related to, or what values the eigenvalues and the pivots take for positive definite matrices. And then before we conclude this, right, we'll quickly talk about the geometry of positive definite matrices. Okay. See, we know that any matrix A does a set of geometric operations on a vector, right? What all does it do? In general, it does 3 operations, right? Scale and flip, mirror, reflect, sorry, yeah. Okay. So if I take a vector x, right, and I multiply by this, let's say I started with this vector, this was x. See, note down that this is a square matrix. So x and ax both are from Rn. So if this is Rn, this is x, ax will also be in the same space. Okay. Let's say I call this y. Okay. Maybe y is like this. Okay. But if A is positive definite, right, then I know x transpose Ax is greater than 0, right? What does that mean geometrically? Yeah? You are almost correct, but what do you mean by lies in first quadrant? Okay, what if, let's say we are talking about R2, right? Let's say this is first quadrant, right? Let's say this was x, and let's say this was Ax. Both of them don't lie in the first quadrant, right? But what did you mean by lie in the first quadrant? Oh, because the individual value, so the scalar is positive, so here both x1 and x2 are positive, that's why you said it's, okay, no, that's not the reason. Inner product, what geometric quantity does the inner product capture? What geometric relationship between vectors does an inner product capture? The angle between the vectors. Yes, cos theta. If it's always positive, what can we say about the angle? What can we say about the angle between x and Ax? Sorry? What the angle lies between 0 to what? Yes, okay. Just write down what we know about inner products, right? So if I have inner product of x with y, then I know this is equal to the 2 norm of x, 2 norm of y multiplied by cos theta. Okay? That means if this is positive, then the 2 norm of x, 2 norm of Ax into, these two are anyway positive. cos theta, that means cos theta is positive. If cos theta is positive, what can we say about theta? No, that's for sine. 0 to pi is for sine. So theta is in fact less than. Okay, so it turns out when you have a positive definite matrix, right? A positive definite matrix can do any amount of scaling and all that, but it will never rotate a vector x by more than plus or minus 90 degrees. Okay, and that is the reason why the inner product or x transpose Ax comes out to be always greater than 0. Okay. And often when you see people talk about positive definite matrices, they will always write symmetric matrices. For example, I don't know, so for example, here I chose to write a symmetric matrix. This is a symmetric matrix. Well, this is not, but still. You will always find that people are only talking about symmetric matrices when they are talking about positive definite matrices. Okay. It turns out it's because we know every matrix A can be written as a sum of two matrices, right? A symmetric and a skew symmetric matrix, right? So I can write this as A symmetric plus A skew symmetric. How do I obtain A symmetric from A? How do I obtain the symmetric part and the skew symmetric part? You remember? This part would simply be A plus A transpose by 2. This will be A minus A transpose by 2. You can verify that this is a symmetric matrix and this is a skew symmetric matrix. It turns out, because we can write a matrix like this, that means I can write X transpose Ax as X transpose A symmetric X plus X transpose A skew symmetric X. And I won't show this, but you can verify. It turns out whenever you have a skew symmetric matrix, right? If A is skew symmetric, then X transpose Ax is always 0. Okay? Skew symmetric matrices, for skew symmetric matrices, X transpose Ax is always 0. That means even if you have a matrix that is not symmetric, right? Whether or not the matrix is positive definite is entirely determined by the symmetric part of the matrix. That's why people will only often talk about symmetric matrices when you're talking about positive definiteness. Okay. And yeah, so this is simply equal to X transpose A symmetric X. The skew symmetric part does not matter. Okay. If skew symmetric, for skew symmetric matrices, X transpose Ax is always 0, what can we say about the geometry of, or the geometric transformation being done by a skew symmetric matrix? For the symmetric, for a positive definite matrix, we said it only rotates vectors by plus or minus 90 degrees. If for a skew symmetric matrix, A transpose Ax is 0, what amount of rotation is A doing to X? Here, Y is, right, and X transpose Y is 0. Y is simply A skew symmetric X. Exactly. Yeah. So skew symmetric matrices will rotate any vector by 90 degrees, right? And that is why the inner product of the vector with a skew symmetric matrix multiplied by the vector will always be 0. Okay. Okay. So that's all I wanted to say about positive definite matrices. We'll now move on to the next topic. The topic of matrix norms. See, we know vectors have norms, right? N vectors, we know how to, we've seen the different p norms for an n vector, right? Norms in general quantify the length of the vector or size of the vector in general, right? But we've also seen that matrices, let's say we're talking about a general matrix like this, we said R n cross m are also vector spaces, right? You can have norms associated, and each matrix is an element in the vector space. So you can in principle define norms for matrices also, because it's just a bunch of numbers. You can ask, okay, for example, if I show you two matrices like this, 1 1 4 1, and I show you a matrix like this, 1000 4000 minus 8000 951, and I ask you which of these two matrices do you think is bigger in some way, right? I will not specifically say what is bigger. You'll say it looks like this is a bigger matrix because the individual numbers are big, right? So this idea of how big is a matrix, if you think of a matrix as an element in a vector space, is a natural question to ask, right? In fact, there is nothing special about a matrix like this. You can think of the matrix as simply a nm vector, right? Essentially, there are nm numbers, right? Whether I arrange them in a column, in a row, or in a rectangular grid, doesn't matter, right? I can simply still define, let's say, norms for these elements in terms of the p norms that we've defined for n vectors, right? So one such norm where you treat a matrix as simply a bunch of numbers, you don't attach any other meaning to that matrix, is what is called the Frobenius norm, right? This is simply the Euclidean norm equivalent of for an n vector, right? The Frobenius norm is for a matrix is often written like this, or the square of the Frobenius norm, I think, yeah. Okay, is simply the sum of the square of all elements. Okay, that's essentially the Euclidean norm. Okay, you can define other norms. You could say, okay, I'm going to define my matrix norm as sum of the absolute values of the individual elements, or I'm going to define the matrix norm as the maximum of the absolute value of individual elements. That would be the equivalent of the infinity norm in the p norm case, right? So this, of course, this is nothing new. This is simply an extension of what we've seen as p norms for n vectors, right? But what is interesting is this is when you look at a matrix as just a bunch of numbers. But we know that there is another interpretation for matrices, right? Matrices represent linear transformation, right? They represent some geometric operation that is carried out on vectors, right? Because I can take a matrix A, right, and I can multiply it by some vector x, which is from Rm, right, and this will produce a vector in Rn, and this vector would undergo some scaling, some rotation, and all that, right? So there is some geometric operation that is being done on this vector x to produce y, right? Matrix norms in general, or another way to define the norm of a matrix, when a matrix is seen as an operator, right, that performs some operation on an input vector, is to ask, okay, how much does my matrix A essentially scale the input vector? Okay, let's say I have two matrices, right? Let's see, and I have, say, two matrices like this, right? From 2 cross 2 matrices. I take any vector x from R2 and I multiply it by this and I multiply it by this. This would simply produce x. Right? So in some way, or in these two cases, right, this matrix scales any input vector more than this matrix, right? And matrix norm is essentially the idea of the matrix norm is that it captures the idea of how much scaling, how much maximum possible scaling does my matrix do to any vector. Okay, that's essentially the idea. Okay. So in this case, this matrix we would say has a higher matrix norm than this matrix, because this we expect our matrix, our vectors that are input to be scaled by a larger amount than this matrix. Okay. That's essentially what matrix norm, the idea that matrix norms capture. Okay, the definition is a little weird, or at least initially it's a little weird. Right? So matrix norms, again, there are different types of matrix norms, and in fact the matrix norms are based on the p norms of n vectors. And matrix norms are usually written like this: matrix with the two double vertical lines. This is simply the pth matrix norm of the matrix A. Okay. And because it's a norm, it satisfies the three properties: definiteness, the scaling property, and the triangle inequality. Okay. This is defined as, okay, maybe, so here matrix norm is supposed to say the maximum possible scaling. That's the maximum I can expect. If I were to choose any possible vector from my input space, and I look at all the possible vectors that come from AX, I ask what is the vector with the largest length that this matrix can produce. Okay, and the definition is something like this. So you take any vector x from the input space. Okay, you multiply it by matrix A. This will produce a matrix in the output space Rn. Here x belongs to Rm, Ax to Rn, as we've defined it as n cross n. Okay, you take the pth norm of this. Okay, and you ask what is the maximum possible value for this. Okay, if I choose any x I want. Okay. It turns out that's not a useful question, because if I can get any length I want here by simply choosing a larger and larger x. So you have to now place some restriction on x. Right? So you say, okay, I'm not going to choose any x I want. I'm only going to choose all the x's with some fixed xp. Right? I choose all possible vectors with a fixed value for xp, the pth norm, right? And then I ask what is the maximum possible value for this for all possible x, that is let's say equal to c. Okay. See, but this again, because you have to account for the length of x, and you divide it by. Okay. One simplification that you will often find is we will say, okay, because we are free to choose xp, we will simply say we will only choose vectors whose pth norm is 1, then this disappears. Okay, and this is okay. You go to the input space, you choose all possible vectors whose pth norm is 1, you compute the Ax corresponding to those vectors, and then you compute the length of all those vectors, and you ask what is the maximum possible length I can get. That is essentially the pth norm, right? And this guarantees that if y equals Ax, right, then the pth norm of y is guaranteed to be less than or equal to the pth matrix norm of A multiplied by, because this is the maximum possible scaling that can happen to my vector. It cannot be more than this, because by definition this is the maximum possible scaling. That means no matter what vector I choose, the resulting vector will always have a length smaller than this. Okay, maybe it's not clear why we have to bother with stuff like this. It turns out when you're looking at systems theory, linear time invariant systems and stuff, this essentially tells you something about the stability of the system. That if, for example, if the matrix norm is less than 1, if the is less than 1, then for sure whatever input goes in will always shrink, it won't grow. But if this is larger than 1, then let's say you input this, it produces an output, and you feed back and you put the same input. Let's say this is 2, right? First time you do this, you get 2 times x, and then you feed it back in, you get 4 times x. So this is useful, right? Even though this looks a little complicated. So to get a handle on this, we'll again go to the geometry, and we look at 3 examples. Basically A1, A2, and A infinity. Okay. Let's say we define the matrix to be A1, something like that. Okay. And if we want to know the first norm, the first matrix norm, right? Okay. To compute the first matrix norm, we need to now choose all possible input vectors of whose first norm is 1. Okay. So that means this is we want the set of, what will that look like here? The first norm is 1. You remember the shapes of the different norms? Everybody is doing this. Sir, diamond, yes, okay. Okay. And what are these points? What values or what are the vectors corresponding to these 4 corners? 1, 0, 0, 1, minus 1, 0, 0, minus 1. Okay, you can verify that in fact all of them have norm 1. Okay. Now, to geometrically understand what this means, right? Let's choose these 4 points, right? We'll call them P1, P or X1, X2, X3, X4, and find the corresponding AX1, X2, X3, and X4. Tell me what the 4 corners are now, right? Okay. To what points do these 4 corners get transformed to by this matrix A? What about the first one? Hey, this is 1, 0, right? Maybe I've drawn it too big. I'll make this smaller. Otherwise, I'll run out of space. That's your x1 equals 1. What does this point get transformed to? 3 minus 1. So that's 3 minus 1, that's here. What about 1, 0, 1? 1, 1, so that will be here. Yeah, minus 2, minus 3. Okay. Yeah, that's here. So, you can simply join these by lines, okay? Because this is a full rank matrix. Lines will get mapped to lines. So, this will be a line. Okay. See, you can already see, roughly say whether the first norm is greater than 1 or smaller than 1 from just this diagram. Why is that? Yes, it's somehow become bigger, right? So that means the first norm is definitely bigger. Okay. Now we go back. So if you choose any point from here, I know the corresponding vector which lies along this figure, right? Now I can ask what is the vector with the largest first norm, because here this is the pth norm. We need to find what is the largest possible one norm, or we need to find a diamond which into which this exactly fits, because that is the largest. So that is the largest possible first norm for the output that can be generated if you choose all your inputs from here. Okay. So what you do now is you take this and you simply expand it. Okay. Expand it till the corner, till your entire figure perfectly fits into that enlarged diamond, right? If you do that, you will find that it sits in a diamond like this. I have not drawn it properly, but here, no, sorry, here. Okay, so if you choose elements from this diamond, where the first norm is 1, all the possible outputs that will be generated will all be within this blue dashed diamond. Okay, and essentially the one norm corresponding to elements from this diamond are essentially is your okay. Okay. Can you tell me what the one norms are for these 4 points? Okay. For example, the P1 norm of all the elements on this blue dashed diamond will essentially be equal to the one norm of this point, because this point lies on the diamond. Okay. What is the one norm of this vector? -3, 1. 4, exactly. So here is there. So what I said was right. The first norm of A is 4. That means this matrix tends to scale up stuff. Okay. So that's for the one norm. Let's do the infinity norm, which is a little easier to do than the. What is the set of vectors for which the infinity norm is 1? What does it look like? X infinity is 1. Square, right? But where are the corners of the square? 1, yeah, that's right. So these are the 4 corners. Now you tell me, under this matrix A, where do they get transformed to? 1, 1, 1 minus 1, minus 1, 1, minus 1, minus 1. One, 4, 0 is it? 4, 0, okay. Again, maybe I've drawn it too big. So, well, I'll say 2, 3, 4. Okay. 4, 0. Okay. Okay. Minus? Minus 2. Here, right? Just one second, I'll make this smaller. What is the next one? -1, -1. 2 minus 1 is it? Okay. This point is it? This point gets mapped here? -1, -1.
-2 -2
Which point? This one or this one? This one, right?
1 -1.
Yeah, okay, fine. 2 minus 2, okay.
And then -2 is 0, so -1
Okay, alright, so yeah, okay, I got it. So it looks like this, I guess. Okay, this thing gets transformed to this. Okay, now how can you find out? What do you do to find out now A infinity? Following the same procedure that we did there. Yes, we simply scale this till it perfectly fits in, and if you do that, you should get a square like this. Well, it might not be here actually. This is longer, so and what is the infinity norm corresponding to the elements on this? What is A infinity? How will you find out A infinity now? See, to find the infinity norm of any vectors on this, we know that these are all elements with the same infinity norm. If you take one element from that square and you compute its infinity norm, that's what you're looking for. We know one element from that, either it's this or this. Yes, or 4, 0. So what is the infinity norm of either one of those? 4. It just turns out that they're equal here. They're not always equal. Okay. You can verify that later on for a matrix like this. Just do the same thing and you'll find that they're not equal. Oh damn it, in this case it might still be equal. So you can try that after class and see that these two don't match. Okay, and in fact, it turns out this is simply equal to the one matrix norm. Is to know the one matrix norm of a matrix, you simply take the columns of A. Okay. Okay. You find its one norm of the columns of A. Okay. And then you find out the maximum possible one norm for the individual columns. In fact, earlier this was -1, right? The one norm of this is 4, the one norm of this is 2, the maximum of the 2 is 4, it's 4. Okay. For this, okay, I'm going to make you all very uncomfortable now. You take the rows of A. Okay. So you take A, I, tilde, no transpose. Okay. You compute the first norm. Okay. And then you take the maximum of all of those. And notice here, it's still the one norm, not the infinity norm. Okay. For the one matrix 1 norm, you take the one norms of the columns. For the infinity matrix norm, you take the one norm of the rows. It might look weird, but it's actually quite natural if you think about it. Okay. And the maximum of that is this. So first row, the one norm is 4. The second row, the one norm is 2. That's why I said if you make this 2, then you will find that for this matrix the one norm is 5. The infinity norm for the matrix is actually 4. Here, We'll conclude after this. Okay. To find the 2 norm, you first have to start with a set of vectors x whose 2 norm is 1, and they will look like this. Okay. You can verify later on that this circle, in fact, I would encourage you to write a program, a computer program, choose points from this circle, compute ax, and then plot those points and see what figure you get. What you will get will be an ellipse, like this. Okay. A circle will get transformed to an ellipse. Okay. And so this is x with 2 norm of x equals 1. This is ax. Now how do we find the 2 norm? Well, you simply take the circle, you expand it till this ellipse fits into a circle of a larger diameter, like this. And the radius of that circle is your 2 norm. Okay. And it turns out that this is nothing but the maximum possible, it might be like this. I think it is like that. Okay. This also you can verify. So for this matrix, okay, write a computer program and get this, right? And find out the circle in which this fits in. Right? And then verify that the maximum possible length for any vector from this ellipse is actually square root of lambda max. Okay. Okay, all right. That's all I wanted to say. Yeah, please go